I love technology. All right, so I believe we're on page 73. We've been looking at this relationship between the growth rates in a fraction equation and how we can use those growth rates to determine where a horizontal asymptote is located. I know we already did the top example, is that right? We got negative 2/3 up here? Okay, so you have stuff written down there. I just want to go over or review the three kind of things we can look for. You don't have to write these down. Okay, I just want to review them for a second. Let's say that the top is growing faster than the bottom, aka you have a higher degree up top than the bottom. If your top is growing faster than the bottom, what does that tell you about a horizontal asymptote? As you travel forever to the left and forever to the right, are you going to level off somewhere, or are you going to go up or down forever? Can we think about if we took a large number divided by a small one, aka faster divided by something slower? Yeah.
How do you grow slow?
You would either grow up or grow down. Okay, so there's no horizontal asymptote in that case. What if we switched it? What if the denominator was growing faster? AKA the degree of the bottom was more than the degree of the top. Yeah?
The horizontal asymptote is at 0.
It's always at 0. Because if you take a small number divided by something massive, you're going to get like 0.000000000 something, which is really, really close to 0. And what if they had the same growth rates, aka the same degree? Yeah. You divide the coefficients. Okay, so we have a horizontal asymptote at the y value of the division of coefficients. Okay, good review, because we're going to see a little bit more of that today. We're actually going to focus more on this growth rate idea, but nonetheless, these three rules are still going to apply. So let's take a look at an interesting case. We can use these infinite limits, okay, approaching positive or negative infinity again to help us find some asymptotes. In this case, we're going to be analyzing a rational square root graph. Rational meaning fraction, square root meaning there's a square root somewhere in there. We have a rational square root graph. How is this graph a little different to some of the other rational graphs that we've seen? Let me find a picture of them to put up here. Okay, for instance, on page 71, you don't have to flip to it, but this is what a typical rational graph looks like if you had a fraction. Okay, typical rational graph. How is this rational square root graph a little different than the typical one? Can you describe something? Do you notice anything? What do you think, Braden?
There's 2 horizontal asymptotes.
Do you see you have 2? Here we only had 1, right? In this case we have 2. So something's interesting going on here the moment we throw in a square root. Okay, so we'll say there are 2 different horizontal asymptotes. And notice how they change. If you trace the graph to the right, you're going to get a different horizontal asymptote than the one you get to the left. Correct? Based off that picture. So let's go ahead and find those. If you were to trace this graph to the left, what horizontal asymptote would you approach? Can we find its value? You're approaching a height of, go ahead, Dan?
-2.
-2, okay. And let's say we approached the same graph forever to the right. The height you are approaching is +2. So what we're going to do is try to figure out where is this -2 coming from, where is this +2 coming from, based off of this kind of growth rate idea, but also analyzing the equation itself. Okay? So take a look. We have the same equation at the bottom in the two boxes. We're going to try to do this by hand. Let's say we didn't have the graph to figure out those asymptotes. Okay, what if we just had the equation? How could we still get those same values? So if we think about this, what is the degree of the top versus the degree of the bottom? If you seriously think about the highest exponent, can we figure out the top degree and the bottom degree? What do we think? Maybe?
Both 1.
Why are they both 1?
Because the x squared is under a square root.
Okay, so in terms of those infinite limits, okay, if we were to actually plug in infinity, subtracting 2 really isn't going to affect the value at all, and adding 1 really isn't going to affect the value at all. So in reality, we're left with a 2x over a square root of x squared. Does that make sense? If you're analyzing infinity, subtracting 2 and adding 1 isn't making a difference. Okay, and Braden just told us that the square root of x squared is the same thing as x, right? And notice how those degrees are exactly the same. 1 and 1. So if they have the same growth rate, we should take the division of their coefficients, bless you. 2 divided by 1 is 2. Didn't we say that was the horizontal asymptote for the right-hand side if we approach positive infinity? Does that make sense? Okay. So we would say there's a horizontal asymptote at y equals 2 to the right. Okay, we were only analyzing the right-hand side of this function. We were only approaching positive infinity. So there's a horizontal asymptote at 2 to the right. If we do the same analysis on the other side, okay, let's say we wanted to approach negative infinity, the top degree is still 1, the bottom degree is still 1. After all, the minus 2 plus 1 are irrelevant because we're plugging in infinity. We're left with 2x over the square root of x squared, which is technically 2x over x. And if they have the same degree, we take the ratio of the coefficients. 2 over 1 is still 2. What's the issue with that, though? What should we have? Yeah. We should have negative 2, right? Didn't we say that up here? It should be negative 2? So why do you think we need to change something? Yeah.
Whenever you do the x squared in the square root, negative infinity times negative infinity would be a positive. And then whenever you take the square root of that, you'd get a positive infinity, but you still have the negative in the top.
I like it, yeah.
Oh yeah, I was just going to say it's negative. You're approaching negative infinity.
You're approaching the negative infinity. Okay, so the fact is that if you are approaching the left-hand side over here, we're going to need the opposite of whatever the right-handed side one was. So this would be a negative 2. So we have to be aware of which side we are approaching. Horizontal asymptote at the y value of negative 2 to the left. Okay, let's try to think about it this way. Technically, I know we're not really doing this algebraically, but technically, if you take the square root of both sides, don't you need a plus or minus in there? So when you analyze the square root of x squared, this is technically plus or minus x. Okay, we can think about it that way. Now, since the first limit on the left-hand side here was approaching positive infinity, we're going to use the plus version. Since the second limit we analyzed was going towards negative infinity, we're going to use the negative version. So really, if we analyze those growth rates, we would have 2 over positive 1 for the right-hand side, which would give us 2. And then over here for the left, we'd have 2 over negative 1 for the left-hand side, which would give us the negative 2. The square root rational functions are a little tricky because you have those 2 different asymptotes. Okay? They might be the same value, but one of them should be positive or negative depending on which way you're traveling. Do we see that? Okay, I think we're going to try another one on the back. All right, so let's just first analyze which direction we are traveling. X is approaching negative infinity, so we are traveling forever to the left. Let's go ahead and analyze the growth rates, because we do have a fraction. We can figure out what's growing faster, the top, the bottom, or maybe they're growing the same. So in terms of the growth rates, again, the -2 plus 1 don't really matter. We have a 3x over a square root of 2x squared. Can we rewrite the square root of 2x squared as something else? Can we simplify that denominator? For instance, can you easily take the square root of 2? Is that a nice whole number? No. So we'll leave that be. What about the square root of x squared? Isn't that just x? Okay. Now again, I know we're not technically taking the square root of 2 sides of an equation, but you should think about this as either a plus or a minus. Which one are we going to use, though, since we're traveling to the left? Are we going to use the positive version or negative version? The negative. Okay. So let's go ahead and write that in there. This is negative square root of 2x, because it's the left-hand side. So let's take a look at the growth rates. Notice how the degree of the top is 1, the degree of the bottom is 1. So if the growth rates are the same, we have a horizontal asymptote at the ratio of the coefficients, -3 over the square root of 2. So let's go ahead and write that. Horizontal asymptote at the y value of -3 over square root of 2, specifically to the left. That's the only side we were checking. Can we think about what the right-hand side would have been? For instance, if this was x approaches positive infinity, what it may have looked like, where that horizontal asymptote would have been? Yeah?
3 over square root.
It would have been the positive version because we would have chose the positive value, so this would have been plus, which means this would have been plus or positive as well. Okay? But it's all about the side you're checking. Do you guys want to try the next one? Okay, be aware of which side you're approaching. Okay, the plus 2x and the plus 2 don't really mean anything. Those aren't the highest powered terms. What do you guys think? Can we get to that stage? Yeah? What do you think from there? Take a look at your degrees, your growth rates. Where's the horizontal asymptote located? Do we even have one? Let's see, what's growing faster, top or bottom? top. So we have something huge over something small. Okay, if you were to plug in infinity, or in this case negative infinity, we would either be going up forever or down forever. Okay, we're not leveling off. So we should be anticipating some type of an infinity. We have to determine, though, is it positive or negative? Are we going up forever or down forever? So this is when we, again, have to pay attention to that side. If you were to plug in negative infinity, would you get a positive value or a negative value? Positive. If you plug in negative infinity up top and square it, that's positive. If you take a negative number times a negative infinity, that's positive as well. Positive over positive is a positive infinity. So graphically speaking, we don't have a horizontal asymptote to the left. Okay, our graph is going up to the left. It's all about those growth rates. Okay, notice how the top was growing faster than the bottom. So we're either going up or down forever. Are we doing okay? All right, we're going to take a look at growth rates a little bit more in depth today. So on the bottom of that page 74, you have this huge table that's filled out for you. And what I want you to do is analyze the different growth rates of these different types of functions. Notice how we have kind of x to a power. We have some exponential functions in here. We have a constant function. We have a natural log function. Do you guys know what that exclamation point means? It's a very excited X, if you want to think about it that way, but mathematically, do you know what it means? Factorial, good. So you know the name of it. Do you know what that exclamation point does? For instance, if I had 5 factorial, what does that mean?
5 times 4 times 3 times 2 times
Good. 5 times 4 times 3 times 2 times 1. So you take whatever value you're starting with and multiply every single number underneath it. Okay? So what this table is showing you is if you were to, for instance, pick the x value of 10 and plug it into these different functions, these are the y values you would get out. Okay, just regular 10 for x, 100 for 10 squared, 1,000 for 10 cubed, so on and so forth. Okay, but what we're interested in is if we were to travel forever to the right or forever to the left, so meaning we want really, really large or really, really negative values. Notice in this case we're traveling to the right towards positive infinity because our x's are getting larger. So the larger our x values get, we're going to analyze what's happening to their y values. Now I used the calculator to fill this out, and for some of these values the calculator was not able to handle a number that big, so I just wrote down too large. What I want you guys to do is rank these functions from slowest to fastest. Okay, 1 being the slowest, 10 being the fastest. Do you think you guys can use the table to figure that out? let's check out the slowest one. So as your x's get larger and larger and larger and larger, which one is the slowest growing, aka the smallest? Can we find it? Good, Dan?
5.
The 5 function. Okay, so that was our slowest. Notice how for the very, very large value of x, you always stayed at 5. Very, very small number. What about the next slowest, or I guess the next fastest? Which one's growing a little bit faster? Go, Braden?
The natural log of x.
The natural log. Okay, so for very large values of x, this one is slightly higher, slightly faster. Can we keep going? It's our third one. Go, Joseph, sorry. The top one. Okay, we kind of have a big jump there from about 7 to 1,000, but that is the next smallest number. So that's our next fastest one. Can we keep going? Yeah?
X squared.
X squared. Okay, a little bit bigger than 1,000. Can we keep going? Now we're getting into scientific notation. Yeah?
X cubed.
X cubed. Next one? Yeah.
X to the 10th.
X to the 10th. All right, and it looks like we're kind of out of options for that last column because all the other ones are too large. So where can we go from there? Were you guys able to reason it through? What do you think, Stevie?
2 to the x.
2 to the x. Okay, so we're going to move into the next column. So for these other ones, we're going to take a look at the other column and see which ones are the smallest from there. So 2 to the x looks like the smallest value from all the other options. So that would be 7, our 7th slowest. Can we keep going? Good. E to the x. Yeah.
4 to the x.
4 to the x. Only ones left are too large, yeah? Factorial x. So it would be 10, and that means this one's 11. How do we do? Pretty good? Okay. So what we're going to do is take these values we have here and kind of generalize what are the growth rates in terms of functions or the names of functions. So we said the slowest function we had here was 5. Do you know what type of function just a number is called? Constant. I heard it. Constant. So the slowest growing function is a constant. In this case, I used the number 5, but if you wanted to use the number 10 or 12 or 2, okay, those would be considered the lowest, slowest growing. So next, number 2, we came across a natural log function. So that's our next fastest growing. Okay, these are slowest to fastest. If we analyze the next few, 3, 4, 5, and 6, all looked like this group. Can you kind of generalize what the function might look like? X to the first, x squared, x to the third, x to the 10th. Don't we kind of have x to some power in all of those? So depending on what the power is, you can determine which one's slower, which one's faster. But we're just looking for function types in this case. All right, the next ones we had 7, 8, and then 9. 10 looked a little different, but notice how 7, 8, and 9 kind of all look the same. We have a number to a power. Is that right? So maybe we have a base to a power. Those are our exponential functions. Depending on the exponential base, you can figure out which one's the slowest, which one's the fastest. Clearly 2 is smaller than 4. So 2 would be growing slower than 4 if you had to compare those. After 9 came our factorial function. And our fastest growing was the x to the x function. Okay? So these are slowest to fastest. What we're going to do on the next page is use this growth rate scale to help us determine what's growing faster, the top or the bottom. Okay, so maybe have that chart handy to help us out on the next page. Do me a favor, for letter C, can you change that to x to the 9th? We didn't really mention roots in that table. Okay. So up to this point, whenever we had a fraction, we had to take a look at the highest power to determine which one was growing faster or slower, but we might not always have a polynomial in the top or the bottom, okay, to determine that. We might have these different types of functions. So we're going to have to analyze the growth rates. If you take a look at part A here, okay, we're traveling forever to the right, so we have to figure out which way are we going. Are we going forever up, forever down, or are we leveling off somewhere? So take a look at what's going on here. If we have x to the 3rd, okay, we can think about that as an x to a power function. And down below, we have a number to a power, so that's an exponential function. Take a look at the growth rates, little scale that we just developed. What is growing faster, the top or the bottom? The bottom's growing faster. Okay, so what's that telling you in terms of the right-hand side of this graph? If we have slow over fast, okay, the bottom's growing faster. Yeah, we're going to level off at 0. Okay, so this is telling us we have a horizontal asymptote at 0 to the right. We have no idea what the left-hand side looks like. We could probably figure it out, but for right now we were just looking at the right-hand side because we were approaching positive infinity. Okay, let's take a look at the next one. How would you classify 999999999? What type of function? Yeah.
Constant.
Constant. How would you classify the denominator? That's a little tricky, isn't it? Does it even matter if we classify it? No, because isn't constant the slowest growing one we have? So it might not even matter if we can determine what the bottom one is. We're going to have the slowest growing definitely over something faster. So this one would approach 0 as well. So again, we have a horizontal asymptote to the right. Okay, we were approaching the right-hand side. What about the next one? What's growing faster, top or bottom? Bottom. So if the bottom's growing faster, we're going towards 0. What about the next one? Which one's growing faster? The bottom. X to the x is the fastest growing one, so in this case it doesn't really matter what's up top. We'd still be approaching 0 to the right. What about E? What's growing faster? Bottom, so we got 0 again. What if we flip it for F? The top's growing faster. All right, so if we have something growing faster up top, we're either going up forever or down forever. We should be anticipating some type of an infinity value, but we have to figure out is it positive or negative. So let's actually go ahead and substitute in that infinity value. If you were to plug in positive infinity up top and down below, would you get a positive value or a negative value? Positive. Okay, so we're going to keep it a positive infinity. So graphically speaking, you don't have a horizontal asymptote. You go up forever to the right. You see how we can still use those three rules even though we don't have polynomials, like just looking at the degrees? Okay, it's all about those growth rates. Okay, so knowing which function is fastest or slowest is a good tool. Okay, the next two are a little tricky. Okay, we're going to check these ones out. Let's go ahead and think about some growth rates. If you're plugging in infinity, okay, well first of all let's think about this. What type of function might we have going on up top and down below? Can we analyze based off of that table our growth rates, what it kind of looks like? Yeah?
Exponential.
Exponential. Okay, so we have a b to the x up top and a b to the x down below. So we have this essentially kind of the same growth rate, right? Okay, because they're both exponential. But let's go ahead a little bit further here. If we thought about plugging in infinity, wouldn't the 8 and the 4 be unnecessary? Because you're adding something to infinity, you're not really affecting the value. So again, this is kind of like negative 3 to the x over 3 to the x. Now in our table, we saw that 2 to the x grew slower than 4 to the x because the base of 2 was smaller than the base of 4. But do you notice how in this case the bases are the same? You have them both as 3. So they are growing at the same rate. How do we figure out where our asymptote is if they grow at the same rate? What are we going to analyze? Yeah.
Coefficient.
The coefficients. So in front of this 3 to the x, we have a negative 1. In front of this 3 to x, we have a positive 1. So it looks like we have a horizontal asymptote at the y value of negative 1 to the right. We doing okay with that one? All right. Now we have to be careful with part B. We are dealing with the same function, but this time we're approaching the left. And notice how the left involves a negative infinity. And typically our first step with any limit is to directly substitute it in. If we did that for part A and we plugged in infinity from top and bottom, the 8 and 4 would be negligible because 3 to infinity and 3 to infinity are huge numbers. Okay? So huge numbers plus 8 plus 4, not really going to do anything. But if you thought about actually plugging in negative infinity into this limit, that's going to change some things because we have a negative power now. How can we change a negative power positive? What can you do? Yeah.
Put it as like minus 1 over 3 in the
Okay.
bottom is 2.
Okay, so you can change a negative power to a positive power by flipping the location in the fraction. We cannot simply ignore the 8 and the 4 in this case because we're dealing with a negative infinity. It might affect the equation somehow, and it's actually going to for this one. So let me ask you this. What is 1 over 3 to the infinity? 1 over something massive. What is that really, really, really close to? Yeah.
Nothing, basically.
Nothing, right? Doesn't that go to 0 in terms of our growth rates? Something small over something huge is always going to be really, really close to 0. Can't we do the same thing down below? We also have 1 over something huge, which is basically 0. So it looks like in this case our limit value is 2. So we have a horizontal asymptote at the y value of 2, specifically to the left. So So graphically speaking, this is another instance where we have two different horizontal asymptotes. If you wanted to draw a picture of this, we need to level off at 2 to the left, and then level off at -1 to the right. So if you wanted to draw a possible graph, I don't know, it might look something like this. Notice how we have two different asymptotes, one on each side, depending on the infinity that we were approaching, either positive or negative. Tricky, tricky. Okay, so be aware of the side that you are approaching. Are we doing okay? Take the silence as a yes, maybe?
Yes.
Yes, okay. So that was it for this section. Really short homework assignment, guys, page 77, and then there's like 2 of them on the back. And you guys have 2 days to review. I gave you some review pages in the actual note packet, starting on page 79, if you want to take a look at those. But then you also have all those ones from the big, thick packet of problems to use. Okay, so if you want to bring that tomorrow, that might be a good idea. All right?